Chemistry time.
Hello everyone. For today's lesson, we will be continuing on with the wave-like properties of light. A simple but very powerful experiment that can display this wave-like property is taking a flashlight and introducing it to a barrier with a slit in it. The light bends or diffracts around it when it encounters an obstacle. In 1801, English physicist Thomas Young performed an experiment that observed how light interfered when passing through slits in barriers. Similar to the previous experiment, but instead of having one slit, Thomas had two slits in the barrier. This became known as the double slit experiment. What ends up happening is the diffraction of light through the two slits ends up producing an interference pattern. You will have a pattern of light with light and dark regions. Waves interfere with one another and can either cancel each other out or increase the amplitude. The two types of interferences that can occur are constructive interferences, which occurs when two waves are in phase or in sync with one another, or the waves can have destructive interferences, where the waves are out of phase with one another and end up canceling each other out. So in the previous experiment that I mentioned, the interference pattern that is observed is a result of constructive and destructive interferences. Up till the 1900s, light was thought to have only wave-like properties. It was described using Maxwell's classical electromagnetic theory, which hypothesized that the oscillating electric and magnetic fields of light travel through space, moving at the speed of light. However, this theory was soon scrutinized due to a number of discoveries that brought a number of classical theories into question, when they failed to explain a number of phenomena such as black body radiation and the photoelectric effect. This was the birth of quantum mechanics, which is the study of matter and light on the atomic and subatomic scale. Black body radiation refers to the spectrum of light that is emitted by heating a solid object. Classical physics assumed that radiant energy was continuous, that is, could be emitted or absorbed in any amount. Scientist Max Planck suggested that radiant energy is only emitted or absorbed in discrete quantities like small packages or bundles. A quantum of energy is the smallest quantity of energy that can be emitted or absorbed. Albert Einstein in 1905 used Planck's theory to describe the photoelectric effect, which is an effect that is observed when metals are in the presence of light. They can emit electrons. He proposed that light must come in packets of energy, which is known as a photon of light. The equation that he used to describe this is energy, which is denoted as E, is equal to Planck's constant times frequency. H, which is Planck's constant, is equal to 6.626 times 10 to the minus 34th joules times second. It is important to point out that the energy of a photon can also be expressed in terms of wavelength by using the speed of light equation. Einstein suggested that light was actually a shower of particles, not a continuous wave, as what was previously thought. This theory was able to describe the photoelectric effect because the emission of electrons from the metal depended upon whether or not a single photon had enough energy, as given by the previous equation, to eject a single electron. This is known as the threshold frequency. If a photon is below this threshold, electrons will not be emitted from the metal because the photon is not strong enough to overcome the binding energy, which is denoted as phi. The threshold frequency is reached when the energy of the photon is equal to that of the binding energy. If a frequency is higher than the threshold, this additional energy is transferred to the electron in the form of kinetic energy. The kinetic energy of the emitted electron is the difference between the energy of the photon and that of the binding energy. Well, I hope you enjoyed the following lesson, and thank you for watching for today.
Chemistry time. never see time.